All right, so we just managed to derive the wall test as an asymptotic hypothesis test for logistic regression. So in particular, we know that at least asymptotically for a fixed beta j naught, it will have level alpha. So now, how about taking this a step further and talking a little bit about the power of the test? So remember, power was defined as 1 minus type 2 error, type 2 error being the error of falsely not rejecting the null hypothesis, that is accepting the null hypothesis when in fact beta j is not equal to beta j naught here. But then look at our test statistic. Intuitively, if there is some different beta j, then we know that this is a consistent estimator. Beta hat j will be consistent, so it will converge to some to whatever beta j is. This whole thing, the square, will converge to some fixed number. The denominator will converge to some fixed number, and as n goes to infinity, pointwise at least, that is, we should see that this goes to infinity. So that's good. Now that means if then I have a fixed cutoff level for my test statistic, that means my type 2 error should go to 0, my power should go to 1. But note, of course, that for fixed n, at least for beta j close to beta j naught, we expect this to be a little bit less optimistic. It's harder to distinguish two values that are close to each other. OK, and I want to study this in a very simple example, or very in a more restricted example than this. So we can actually make some calculations explicitly. And for this, let's put everything in 1D. And let's assume that our covariates are actually Bernoulli 1/2 random variables. So that means there's only two possible values, 0 and 1. And they occur with probability 1/2. So in particular, this means that if xi is equal to 0, then the yi's I will observe. So the yi's are going to be Bernoullis with this probability. So now I can not write any, I'm allowed to not write transposes because I'm in 1D. So that means if xi is 0, then I'll get a Bernoulli 1/2. That means there is no influence on, so if it's 0, then there is no bias toward any outcome. And if beta is not equal to 0, and I have a draw of 1 for the xi, then there's some bias for the outcome, and that's given by this formula. And for the remainder, let's assume that beta is not equal to 0. I want to study type 2 error. So, and let's take one step back and think about where this came from to make it to facilitate writing down the something that will guide us toward understanding the type 2 error. Namely, we started our calculation for the wall test by some asymptotic normality. In particular, so the inverse, I can now, this is a scalar, so I can write it as multiplicative, square root n times square root I hat beta hat times beta hat. This is what led us to this test statistic in the end. So, and we know that if the underlying beta is not 0, oh, sorry, and I forgot to mention, I want to assume that beta naught is 0. So the only thing I'm testing is my coordinate relevant or not from my model? Right, and that's why I assume beta is not equal to 0 there. So and then if this happens, then this will not necessarily be asymptotically normal. What will be asymptotically normal is beta hat minus beta. So let's subtract off beta and add it back again. And now I'm going to be a little bit sloppy about justifying my steps here. in particular, I want to say that, OK, this converges to a normal distribution, but then I'm adding a mean that's beta times square root n times square root of the estimated information. And of course, this goes off to infinity. So there's no good limiting distribution here. But I want to say that for large n, this is roughly distributed like a normal distribution with variance 1, because I already multiplied by square root I hat. And then mean that's given by this. And let's also substitute the population information in here. So of course, for finite samples, this will not exactly be true. But it should be guiding us toward understanding what's happening. So it will roughly be equal. If n is large, this will almost have converged already to a normal. So it will roughly look like a normal that's shifted by this amount. And this amount is also just an approximation. But this is roughly what should be happening. If you want to make this completely rigorous, you should think about using concentration inequalities, essentially, saying how well does this concentrate about its mean, independent of that it has to have a certain distributional form. But for our purposes, let's just think about it as this looks roughly like a normal with a certain non-zero mean. And if the null hypothesis were actually true, then the mean here was 0. Then the mean here would be 0. Then beta would be 0. So, and if we want, we can also write down the approximate limit distribution of the test statistic. So TNW will then be n times beta hat squared times I hat beta hat, which is the square of this expression here, because I subtracted and added back in the beta. And this is just the distribution that I get from squaring a distribution that looks like this. And this has a name. We call it a non-central chi-squared distribution. And the mean or the non-centrality parameter is, by convention, the square of the mean of the normal that you take and then square, with 1 degree of freedom. So we might or might not have seen this in class, but it's not super important to understand exactly what this distribution looks like. The important part is intuitively knowing that that it comes from some normal distribution that has its mass somewhat concentrated about its mean. So this chi-squared will have its distribution somewhat concentrated, or its mean will be 1 coming from the variance plus this mean squared coming from the mean contribution. In other words, this will be a distribution that's somewhat concentrated about n times information of beta times beta squared, maybe plus 1. But it has a huge chunk of mass there. And if this thing moves out to infinity, so now let's check. So for fixed beta, this is a fixed number, this is a fixed positive number, and they're both non-zero. And then I multiply it by n. So as n grows to infinity, this goes off to infinity. So this distribution grows larger and larger. And if I have a fixed cutoff, then again, I should have power going to 1, type 2 error going to 0. So everything's fine, right? So let's simulate some data from this. And I'm just going to plot the value of the test statistic here. So I start off with some beta. I choose n equals to 1,000, so not small. And I plot my test statistic versus the beta. And you see that it nicely grows. It's a little bit harder to distinguish the values that are close to 0, close to beta naught, but the other ones grow. So that's cool. But this happens when I do this for larger beta. So actually, it looks like the test statistic is getting smaller again. Do you have an idea why this could happen? So in order to think about this, well, we know that it should roughly look like this. Maybe it's a matter of concentration. Maybe my roughly equals here were a little bit off. So let's plot this quantity instead. And we see that indeed it was a little bit off. If you look at the beta equals to 6, I sometimes get a test statistic down to 0. Well, this is just one random realization. It can happen. And maybe it's also getting a little bit harder for my solver to actually solve it if my beta is very large, or it's not very large, but if my beta is very large, those probabilities are very large, are very close to 1. But this is the curve, and we see that it still has a maximum, and then it goes down again. And this is something that we did not like. This is something we tried to make a point of when thinking about estimators before, when thinking about hypothesis tests before. We want to make a point out of having certain monotonicity. We wanted to say, well, if the true beta j is kind of close to the null hypothesis, then we can stomach that it's harder to distinguish the two. But if they're far away from each other, we kind of want it to be easy to distinguish also in terms of the test statistic. We want to have low p-values, for example, when we plug it in. So this is quite an undesirable behavior. Let's try to understand why it happens. So we already saw that this is not a bad description for what's going on. So what could be happening here? What could be the problem? Beta squared, well, grows, so everything should be growing, right? And n is fixed in the plot that I showed you. It's large but fixed, so that this approximation makes sense. So the only thing that can go wrong is the information of beta. And indeed, if we look at this expression, there are some exponentials there. So let's first write down the information, what the information is in our case here. So this is going to be the expectation. So I'm just taking the expectation of this estimator that we had. So this is 1d. So instead of xik, xil, I can just write xi squared. And then e to the xi beta divided by 1 plus e to the xi beta squared. OK, so and now we see why I picked this specific model, because we can actually calculate this explicitly. So either xi is 0, then this whole expression is 0 because of xi squared here, or xi is 1, in which case, so we have 1/2, the probability of it being 1, times 1 times e to the beta divided by 1 plus e to the beta squared. We can already kind of see that something is going to go wrong here, because this denominator goes to infinity if beta goes to infinity, and it goes to infinity faster than this exponential also if I multiply it with beta squared. In order to justify this somewhat rigorously, let's briefly recall L'Hopital's rule from calculus. This is just a neat little trick that allows you to think about limits of quantities when both quantities go off to infinity. So in this case, we'll have, let's forget about n because n is large but fixed. We'll have this quantity here to analyze, which is, we just calculated 1/2 times beta squared times e to the beta divided by 1 plus e to the beta squared. So now we know what we wanted. Beta squared goes off to infinity. Beta squared times e to the beta also goes to infinity, but the denominator does as well. It's 1 plus e to the beta. So L'Hopital's rule works like this. When you have two functions, f of x, g of x, and you're interested in some limit, x going to some limit c, c might be infinity. So for our purposes, infinity is fine. And if f of x goes to infinity, g of x goes to infinity, and f of g are both differentiable, then f of x, so then the limit as x goes to infinity of f of x divided by g of x is the same as the limit of x going to infinity, f prime x divided by g prime of x. And actually, let's write it down in terms of any c, and c can be infinity. If those limits are, oh, I forgot to write g of x going to infinity. If those two limits are true, so if those go to infinity, you could also write it as, you could also apply it if they go to 0. OK, and let's try to apply this here. So I have this. Both numerator and denominator go to infinity. We checked. So let's write this in terms of a tilde, but this tilde does not mean distributed, as it just means asymptotically equivalent, which means having the same limit as beta goes to infinity. Right, and I'm only restricting to the case of beta going to infinity. This corresponds to the plot that we just saw. OK, let's differentiate the numerator. If I do this, then I get 2 beta e to the beta, first differentiating the first term, plus differentiating the second term, beta squared e to the beta, divided by 2 times 1 plus e to the beta, and differentiating e to the beta. OK, not quite there yet, because numerator and denominator still both go to infinity, but at least we can simplify it by dividing by e to the beta. So this is equal to 1/2, or 1/4 actually, if I carry the additional 2. 2 beta plus beta squared divided by 1 plus e to the beta. Goes to infinity, goes to infinity. So let's use L'Hopital again. So let's call this star. And here I'm using star, and here I'm using star. Gives me 1/4 times 2 plus 2 beta divided by e to the beta. As beta goes to infinity, this still goes off to infinity. But how about one more application? So I can divide by the 2. And then we get 1/2 times 1 over e to the beta. And finally, as beta goes to infinity, this goes to 0. And this is what we wanted to see. So actually, the non-centrality parameter here goes to 0. Which means, in other words, the plot we're seeing is exactly what we expect to happen. And this explains why the wall test is maybe not the best choice, at least not in all possible beta regimes, for logistic regression. And note that this argument can be made more general. So this does not only happen when I have these Bernoulli inputs. You can write this down quite generally. But it needs some more attention to this inversion here, and this is why I decided to only look at it in the Bernoulli case. But it will happen generally. Now, you can think about the case that I omitted, kind of. What happens if beta goes to -infinity? We also expect this breakdown to occur, this power vanishing as beta goes to -infinity. And you should be able to show it also using L'Hopital's rule.